All right, hello everyone. I'm Vincent. I'm working for Google with the Android KVM team, and we are bringing a solution of protected computing for Android. And today I'm going to talk to you about how to trace things that are happening in the hypervisor we are using for this solution, and especially how to integrate this with Ftrace. And of course, when I mean Ftrace, I mean TraceFS.
Thank you.
All right, before we get started, quick recap. Very simply, how KVM works on ARM64. So you have two modes. So back in the day when nVHE was introduced, the host kernel could not run at EL2, which is the execution level 2, where the hypervisor usually runs. So what happens then is the host was running at the normal kernel mode, but there were like a tiny piece of code called the world switch that was basically just allowing the host kernel to talk with the guest. But then, later on, from 8.1, the nVHE mode has been introduced, nVHE for virtualized host extension. I hope I got this thing right. And then the host kernel can run at EL2. So it's great because it's really fast, but the problem, as you see here, is you've got like a hierarchy between the guest and the host. This is a problem when you want to do a protected VM, where you don't want the host to be able to inspect what's happening into the guest. So looking at this, it seems that the old mode, the nVHE, for non-VHE, seems quite interesting. So what does pKVM do? pKVM is using this mode, the old mode, and extending a bit. One of the major things is that it brings stage 2 translation between for the kernel, the host kernel, and everything is now handled in the world switch, which is now kind of a protected hypervisor, and which means that the hypervisor makes sure that at any moment the host kernel cannot see anything which is happening in the guest. Okay, it's all great. So we have now our protected solution. And if you want more details on that, feel free to watch the great presentation that my colleague Quentin made at KVM Forum this year. The link is on the slide. All right, now we've got our hypervisor, but remember it used to be a tiny piece of code. Before I forget, that's something we're going to see later. One of the important bits is we're going to have the virtual address space of the host is separated from the hypervisor virtual address space, and that's something important we're going to see after. All right, so now I can go on. The code has been growing more and more. So it used to be like something very simple, but now it handles locks, it handles the stage 2 page tables. There's a lot of memory sharing happening, donations coming from the host for the guest giving back some memory to share for like device simulation, for example. So yeah, the code is growing, and we need to know what's happening there, which leads to we want to trace what's happening here. If for example, a completely random example, you receive unknown hypercalls and you want to know what's happening, tracing is here to help you. All right, before we continue to how to trace in the hypervisor, here's a quick recap about how the Ftrace ring buffer works. So here's a simple ring buffer. I put rails between the page for an analogy later, and also we love trains in the team, so that seemed appropriate. So simple ring buffer, you have a writer, which acts like a train, you cannot stop, and you have a reader. In the first reading mode, a non-consuming mode, well, you just start at the head, you read until you reach the writer. All good. If the writer catches you, though, well, you're just gonna bail out. You cannot be sure that your data will not be corrupted. It's quite annoying. So there is another way of reading the ring buffer. To do this, you just take another page, and you're gonna swap this page with the one you want to read. So to do this, you connect your page to your ring buffer. And then atomically, you're gonna just switch, you're gonna reroute your writer train from one rail to the other. It's done with a compare exchange, so it's atomic, and of course there's a bit of things to make sure that you are sure that before you switch, the writer is not already on your head. Now, your writer is routed to the new page, and you can remove the old rails, and you've got the head taken out of the ring buffer, and you can do anything with it. For example, it enables zero copy if you want to send it over the network, or that kind of things. All right. So what problems do we have here? I should mention this is called a consuming read because the data that you read after removing the page are just gone. Okay, what problems do we have here? Well, the first thing is that the rails, quite unsurprisingly, are just pointers. And those pointers are in the kernel virtual address space. Also, all the mechanism to ensure the atomicity of when you do the rail switch, it's just flags embedded into those pointers in the first 2 bits. And this is a problem for us because, as mentioned earlier, the kernel virtual address space is different from the hypervisor address space. So it would mean we would have to do conversion all the time from one way or the other. So it's quite cumbersome, and also it's, in terms of performance, pretty bad. Also, the thread model says that we cannot trust anything coming from the kernel. We cannot trust that the kernel will not try to modify those addresses so that the hypervisor will write suddenly to somewhere else, to some places it's not allowed to. So it's not something we can use. So overall, it's impossible for us to share the links to those rails. So solution for this, let's go back to a simple ring buffer. So we have the ring buffer allocated in our kernel, and what we can do is simply serialize things, or more like serializing all the metadata we need to describe the ring buffer. We put that into a packet, and we send this to the hypervisor. There, the hypervisor can do all the translation it needs. It can verify that the pages can be mounted. It can protect them if necessary, and it's going to recreate its own view on the ring buffer. Here on this graph, so the pages in green are shared between the kernel and the hypervisor because that's where the data are found. But all the links are private and separated. So you have the same ring buffer, but the kernel has its own view on the ring buffer, and the hypervisor has also its own view. But now, well, we still need to share data, right? At some point, they need to communicate. The kernel, which is the reader, needs to know what's happening in the buffer. Did anything happen? Get statistics, and also which page is which. So actually, as I said, we are already sharing memory. We are sharing the pages where the data are stored. We could put them in a header. The problem is that this header has been there forever, and user space tools such as trace command are aware of the header. So for ABI compatibility, we cannot really extend. It's also quite packed, quite small, and I think even one of the counter has been already repurposed with a few bits inside. So we cannot put many data there. So another solution is just to introduce a footer. It's pretty easy. The writer just needs to know the existence of the footer and never write past this data. And at the beginning of the page, you know how many events you have and what's the size of the event. So you can just stop at the right moment and keep this data. All right, so now we have a different view. We have a way of sharing data between the kernel and the hypervisor. But what about the rail switch? Well, it's pretty simple in the end. So the reader, whenever wants to read something in a consuming way, the reader can just ask the hypervisor to do the rail switch. So for this, there's an hypercall. I call it here just swap reader to it. So the reader issue the hypercall, and then the hypervisor will do all the atomic operations to reroute the writer. Once it's done, and it's going to try until it manages to swap the right page. Once it's done, the hypervisor can just update the metadata in the footer, says this page is now your reader page, this page is now your head. This is the statistics, this is the number of events you missed if you did not read fast enough, and all that kind of things. And finally, you just return to the kernel, and the kernel can just read the metadata and update its own view. And now the kernel has a page. It knows that it's out of the ring buffer, and it can just consume it. All right, let's try to summarize everything with this timeline. You have on top of this timeline the kernel part, on the bottom the hypervisor part. I did separate something which is quite generic operations, as this could be applied to any external writer, that's how I called it, and you have the bit which is really pKVM specific. So you allocate a ring buffer with the regular ring buffer allocation, nothing really fancy here. You serialize all your informations, and you send this to your hypervisor. The hypervisor deserializes everything, and it installs its own view on the ring buffer. And from there, the ring buffer is ready. The hypervisor can start right over there. Now the kernel wants to know what's happening into the ring buffer. So we can issue an hypercall, which is just asking the hypervisor to update the statistics. So then the hypervisor, will just write into the footer page how many events have been written, how many pages have been touched. And from there, the kernel can know that stuff happened on the ring buffer, and the kernel wants now to be able to read there and do it in a consuming way. So the kernel can ask to swap the reader page with the head page, which the hypervisor can just do. Once it's done, you're sure that the new reader page is out of the ring buffer. You're sure that the writer will not pollute anything there, and you can simply read what's happening. You can consume the reader page, and here it's like really a generic ring buffer page. So all the functions that are used for host tracing are just working exactly the same way. And of course, then you start again whenever you want. So you've got this polling to check what's happening on the ring buffer, and so on. So that's all for the low-level part, so the ring buffer part. Now I'm gonna talk a bit about the user space bits. In terms of user space interface, what seems to be the best approach is to have simply a separated folder, and in this folder, we replicate simply the interface, the host tracefs interface. You have your file tracing on, you have your file trace where you do a non-consuming read, you have your trace pipe where you do a consuming read, the same version for per CPU, and you've got the same for the events. Why duplicating all this? Well, as we saw, it's separated ring buffers with different capabilities, different features, different sizes, so it doesn't really fit the host interface. Also, it's quite interesting because the host already supports instances, so it means that the user space tools already know that you can have this duplicated interface into a separated folder. So it's quite easy then to just take trace command and to tell, okay, that is your folder, just create a trace file out of this, and this is fully compatible. And that's it for the user space interface. A few words about the current status of this work. I haven't mentioned nested writes. This is because we do hope that it's not going to be needed. This is, in my opinion, the biggest source of complexity into the ring buffer. So I do hope we won't have to implement it. Reason is we don't do preemption at TL2. We don't take IRQs at TL2. We only can potentially take SRRs, but they could be masked. So yeah, no nested writes on our side, and we hope it's not going to be necessary. We already have a functional proof of concept. It's been used on the Pixel 7, which is the latest Google phone released last week, I believe, for both debug and profiling. Debug to see, like, do I have a memory leak here? Can I trace where are the pages going? And profiling to see, for example, how much time we spend in EL2, because currently there's no way for the kernel to know exactly when it's preempted by EL2. And in terms of production, we do hope to have these features available and also propagated to Perfetto for the next Android release. And that's all I have. Upstream too, of course. Yeah.
Cool. Thank you, Vincent. I can already tell there will be several questions from the kernel corner of the room. Can we get the red mic on? Thanks. It should be fine, don't. They're just.
Hello?
Okay.
Hey? Okay.
It was okay.
I think it's working.
Okay. Have you checked that what are your trace interface? Because that it seems that very similar things you are doing. What are your trace? We made it for the maybe 10 years ago. Yeah, using the splice in the guest, so that the guest will splice the trace file ring buffer page to the virtual link, and the host side you can get the page to the file. Yeah, I think that you maybe forgot that, but we already have that on the trace command side.
I think you can. You are talking about tracing guest, right? To trace
Yes.
how to get. So yeah, I'm quite sure it's working. Here, the idea is really to trace what's happening in the hypervisor in the highly privileged code,
Okay.
and all the mechanisms allows you to get that data directly in the host.
So I think, if I remember, because I had a discussion with Vincent before, in the beginning of all this, and I guess the big issue here is the fact that the guest, we do that, but the guest has its own tracing. So the guest is doing tracing and passes information to the host. Yes, exactly. The problem that he's just solving right now is the hypervisor has no tracing. He's implementing the tracing in the hypervisor. So there's three components. There's the host, the hypervisor, and the guest. And none of them, or the hypervisor has control of the other two, but the host and the guest have no access into the hypervisor. So now the hypervisor needs to implement tracing in a very limited way. So that's what he's doing. He's implementing the tracing so that now we're basically what he's doing, he implemented tracing that we could do what we did with the guest and host.
Okay.
Does that make sense?
Yeah.
Did I basically explain that?
Yeah, that's perfect.
Okay.
Cool.
Thank you.
We got another question in the back. Could someone pass or I'll grab the mic.
Hey, does it work? Oh, yeah. Great talk, first of all. Thanks a lot. Quick question on the user space interface. Is the ABI of the trace pipe the same of user space? So from a user space viewpoint, does it look like an instance or the ABI is slightly different? I'm asking because at some point you showed some footers and was not clear to me if they're exposed to the...
Yeah, okay. Those footers will not pollute the user space.
Okay.
They are just there like internal things so that the host kernel can knows what to do with the pages. But then in the header of your page, it still says like you've got, you do have X events, and you just know that you don't need to read past those events.
Gotcha. So if we had support for the instances in Perfetto, you would expect that from the user space viewpoint to just work because that looks like a... Great, thanks.
Yeah, the main thing here is the fact that the API for the interface for the ring buffer is only with the header. It really doesn't care about anything, and it says, well, here's the commit, here's how far things are, and then with maybe exception of the missed events. But anything after that, it ignores. So if you support that interface, which is what it is, you could attach anything in the back end. So you can even expose that to user space, and as long as you don't depend on it, you should be okay.
Okay, I got a question over here.
Hi. Are there any concerns with timestamps potentially not being the same between the hypervisor and the host?
Yeah,
Do you need to synchronize time?
have not mentioned the timestamps.
That's why I asked.
How it works? Well, we are pretty lucky on the ARM architecture because we actually read the same clock in the hypervisor as the default clock in the kernel. Of course, if you are trying to change the default clock in the kernel, you might run into some problems. I don't remember what are the clocks that the kernel can support, but basically the default clock that you have in the host is the only one that will allow you after to interleave the traces. So there's also support to be able to decode the counter and to make a timestamp which is synchronized with the host. So if you are running a machine, you are on one hand tracing the host, you are on the other hand tracing the hypervisor. You get two trace files, and then trace command can just interleave everything because it supports already taking several files at the same time.
Thanks.
I was just about to make sure we confirm about that because we already have all the information. If you have the multiplier and shift and all that, trace command takes the metadata. So as long as, if everyone's using like the TSC from the host, because I know the guests, at least on x86, the guests could have a different TSC, but that information is exposed by KVM debug, and it tells you how it changes it. So as long as we have access on how all the clocks are being manipulated, we could then synchronize everything. Anyone else?
I have one question.
I love how it's on both ends.
So that that interface will be what's it, the one special instance in from the viewpoint of the host side. Host, yeah.
Yeah, it could be seen as a special instance. Honestly, I'm completely open as per like where to put it. But yeah, when I meant instances, I meant more like the trace command already supports something which is roughly the same. You just have a different folder with all the files you need. So as long as the hypervisor tracing exposes the same files with meaningful command, it's going to be compatible. That's what we are aiming for.
So that it will be a new folder.
It would be, yes.
Okay.
So I don't know if I can. Yeah, I don't know if it's really clear. You have your tracefs root in tracing, and then that would be like a separated folder that I called hype here. It could be anything really. And then inside you have you duplicate your files, the same as you have in tracefs, the tracefs root.
Okay.
Cool. Any more questions? All right. In that case, thanks, Vincent.